some fundamentals of electrical engineering. And we were on fourth module, that is signal systems, and we were looking at Fourier series. In the earlier session, I suppose the general basics were discussed, and in this case we'll go a little deeper, but this is more interesting because we are also having a look at the discrete time Fourier series with their own representation. And in this representation, an interesting aspect happens to be that since the signals happen to be discrete in nature, the Fourier coefficients will be periodic in nature. And similarly, any periodic quantity will also have discrete Fourier coefficients. So the alphabets that are connected together in this context is D and P. If the signal is discrete, the Fourier series coefficient will be Fourier series as such. Fourier Transforms also will be discrete, will be periodic in nature. Okay, so let's look at the first question and understand this deeper. In the first question, the discrete time Fourier series representation of a signal xn is given with period as capital N is written as xn. So now the Fourier series representation is given as xn equal to, as is very clear, there are only discrete numbers, that is k equal to the summation, that is for the function to be explained, we have only the coefficients going from k equal to 0 to n minus 1. So it depends upon the number of signals that are there in the samples that are there in the function. Okay. So, and it's explained as ak e raised to j 2kn pi by capital N, where n refers to the period of a discrete function. Okay, so discrete time periodic signal with period n equal to 3. Okay, has the non-zero Fourier series coefficients. So very few coefficients are non-zero. They are described as a minus 3 equal to 2 and a4 is equal to 1. Okay, the signal is, so what is the signal? And so options are given. Point number 1. The periodicity of the signal is 3. Okay, or in other words, the signal xn will be described by when k equal to 0, then k equal to 1, and k equal to 2. 3 minus 1 is 2. Okay, so there are only 3 coefficients. Okay, and what are these coefficients? They are described and they are recurring, or they are periodic in nature. So we have a minus 3 also talking about a minus 3 plus 3 or a0, or a minus 3 minus 3, a minus 6, and so on and so forth. So in all these contexts, that is a minus 6, a minus 3, and a0, and even beyond, the coefficient is equal to 2. Similarly, a4 or a4 minus 3 or a4 plus 3 and beyond. Okay, so that is a4 or a1 as also a7 are all equal to 1. Okay, because it is recurrent and periodic in nature. Okay, so now we have 2 coefficients of the 3 that are required for explaining xn as equal to a0 is equal to 2, a1 is equal to 1, and a2 equal to 0, because all the other coefficients are 0. Okay, so and that's what is given in the table. Okay, so now we can write out xn using these coefficients as equal to a0 plus a1 into e raised to j. In the earlier case, e raised to j0 comes, so we have a0 only, and then we have a1 e raised to j 2n pi by 3, where capital N is equal to 3 plus 0. Okay, so and a0 and a1, if you replace, you have 2 plus e raised to j 2n pi by 3. Okay, so far so good. So now let's see if we can find out from the given options A, B, C, D, which one matches 2 plus e raised to j 2n pi by 3, which is the function xn as explained by the Fourier series coefficients. Okay, so now we see that we have 2 terms in each of these values given, and the first term is all constant and equal to 2 or 1. Okay, and in the second one we have a constant equal to 2, then we have e raised to minus j 2n minus plus etc. of 2 pi n by 6, and we also have cos 2 pi n by 6. So this cos 2 pi n by 6 we have not got in our series. In our explanation. So what do? We try to find out what is cos 2 pi n by 6. So cos 2 pi n by 6 or cos theta is e raised to j theta plus e raised to minus g theta by 2. Okay, so we see the so cos 2 pi n by 6 is written as e raised to j 2 pi n by 6 plus e raised to minus j 2 pi n by 6 by 2. So now we have a 2. Also, we have two exponentials with just a change in sign. So if the one exponential multiplies another exponential with the same exponent but with the change of sign, then we are going to have e raised to 0, and that's equal to 1. So from the coefficients that we have, we see that to generate 2, we can have 1 plus 1, and that is possible from options B and C, because we already have a 1, and so 2 by 2 will cancel, so we get 1, and one of these coefficients should disappear as equal to e raised to 0. Okay, so let's see, do we have any e raised to we have in B option, we have e raised to j 2 pi n by 6. So if it multiplies to e raised to minus j 2 pi n by 6, we have e raised to 0, and then so that's only one term of it, and so 2 multiplied by that particular term by 2 gives us 1. So 1 and 1 2. So that's okay. Now what is left is e raised to j 2 pi n by 6, which also by 2, e raised to j 2 pi n by 6 by 2, multiplying again 2 e raised to j 2 pi n by 6, we see that it's equal to e raised to j 2 pi n by 6 into and e raised to j 2 pi n by 6 is the same as equal to e raised to j 2 pi n by 3. Okay, so it's very easily through a 3-step version this problem can be solved. So what do we have? So B seems to be the correct answer. So what do we do? What is the period? What are the coefficients? Then what is this additional cos 2 pi n by 6 doing there? Okay, and so just manipulation and you get to the answer. Let's move to the next one. Consider gt is equal to t minus t with the upper cap. Okay, where t greater than 0, and we also have t minus t with an under cap. And so that's the explanation of GT otherwise. Okay, so for t greater than 0 we have a different kind of expression, and what are these? So t with an under cap represents the largest integer less than or equal to t, and t with the over cap denotes the smallest integer greater than or equal to t. So they are on either sides of t equal to 0. So what happens when you have the largest integer less than, when you deduct it, it's the same as equal to, okay, the largest integer deduction means that you're getting what is called as t minus 1, and this t minus 1 happens at ut minus 1. This is the same as equal to what we were seeing earlier, wherein we see that you have this this ramp, the slope equal to 1. It starts off at t equal to 0, then it ends inside a pulse of width equal to time unit equal to 1, and then it restarts, and then so it continues on t equal to 0, greater than t equal to 0 axis, as is shown in the figure. On the other hand, in the other case, we are having integers greater than or equal to t. So now we are having the under cap represents the integers less than or equal to t. So we see that now we are having the same kind of slope, but at the same time the values are negative. Why? Because we are deducting larger values. So we are having what is called as the same kind of slope, that is positive slope, but the amplitudes are going to be negative, or in other words, they are going to be the entire waveform is going to be a rate as is shown in this diagram. Okay, so what is asked is the coefficient of the second harmonic component of the Fourier series representing GT. Such a situation, such a diagram or such a waveform GT cannot have Fourier series coefficients. Why? Because it is not periodic. Okay, because they happen to be different on both sides of t equal to 0 axis. So they are not. It's not periodic. The waveform is not periodic. So the second harmonic coefficient or whatever coefficient will not be equal to 0. So option A is the correct option. Okay. Moving on to the third problem, what do we have there? It seems that we have a small filter H omega, of which the frequency ranges from this low pass filter minus 500 pi to plus 500 pi. Okay, and what is given is that the signal xt is equal to k equal to minus infinity to plus infinity minus 1 raised to k delta t minus k by 2000. So let us look at the signal first. Okay, and what is written further is that it is passed through an LTI system with frequency response h omega as shown in the figure below. Okay, and the Fourier series representation of the output is given as. Okay, so these are some of the things that we require. First and foremost, what is the filter? The filter is a low pass filter, and its frequency is ranging between -5000 pi to +5000 pi. And what we have here as the signal which is passing through this filter, it's xt. It's alternatively +1 and -1. That's an impulse. Okay, as is shown here. And then we also have it being spaced equally with the spacing as given by t, capital T as equal to k by 2000. So k and k goes from -infinity to +infinity. So it's no doubt a very periodic signal, but the values alternate, and between two signals the placement of time is equal to capital T as given by 2 by as given by 1 by 2000. Okay, so we have, because k equal to 1 tells us that 1 by 2000 on the other, but at the same time, since the signals are alternating between -1 and +1, the period is given by 2 by 2000, or in other words, omega 0 is equal to 2000 pi. Okay, so now when we have such a signal, only obviously this is an odd signal, and so the odd signal, so it will have odd multiples of omega naught only in the Fourier series representation, which means that we should have 3 to the 6000 and 6000, then it should be 5 to the 10,000 and so 4000 is removed. Okay, I'm sorry, no even multiples are allowed, so only odd multiples are allowed because the signal is odd in nature. So we see that we remove option A and B. Okay, and now since we have a filter which will pass on what is called as the area of the signal, so we have 2000 and 4000 pi on other sides of 4000 divided by pi. Okay, so 4000. So the option C is the option which gives the Fourier series representation of the output. Okay, moving on to the fourth problem. The signum function is given by, signum x is equal to x by amplitude of x wherever x is not equal to 0, and when x is equal to 0, then it's equal to 0. Okay, so it shows us that you have to whatever be the amplitude, signum function will give you only 1, because it will be either +1 or -1, because the quantity, the amplitude of the signal is divided by its amplitude. Okay, it's amplitude only. Okay, so so now let's read further. Fourier series expansion of signum cos t has. Okay, so now it's a cosine function that we want. Okay, and cosine function, when you divide by its magnitude with only its magnitude and not its sign, then it's obviously a square wave, because each of these magnitude is each of the constituents of the cosine curve is going to be divided by its magnitude. So you're getting a square wave. Okay, a square wave. Okay, and since at x equal to 0, since we have cos 0 as equal to 1, so we see that we are having a square wave. Not only that, it has whenever it's equal to, whenever the value goes to 0, it's equal to 0, or we are having a square wave which is an even function with the half-wave symmetry. If it's half-wave symmetry, then a0 is equal to 0, or sine components are, because it's even symmetry, the sine components are absent and the even harmonics are also absent. Okay, so what do we have here? The Fourier series expansion of signum cos t has only sine terms, no. Only cosine terms, no. With all harmonics, no. Only sine term, only cosine term, that's right, but with not all harmonics. Okay, even terms will be absent. Only sine terms with even numbered harmonics, no. Only cosine terms with odd numbered harmonics. Okay, so that's right. Okay, so now let's move to the fifth problem. So it's a triangular wave, and it's obvious that it is an odd signal, because it's an even signal, because it's arrayed similarly or identically on both sides of t equal to 0 axis. Okay, function t is explained in this manner. And what is its period? Its period is very simply the same as equal to, so we have 2. Okay, so 2 time minutes. Okay, so what is asked is Fourier series of the waveform ft shown in figure S. Okay, so it's a triangular waveform with even and half-wave symmetry. What do you mean by half-wave symmetry? Shift the signal by half its period and then reflect it. Okay, and if you get the same identical signal shape, then you are having half-wave symmetry. So in this case, it's obviously half-wave symmetry because half the period is when either all of its positive wave or its negative wave. Okay? So it's obviously it will have only cosine terms because of the even symmetry. And so from amongst the answers, only one option C has cosines with it. Another important aspect that you can add to it here happens to be that at t equal to 0, at t equal to 1, at t equal to 2, etc., how much does it converge? For convergence to happen, it should all be, so all the quantities that are given here should be positive and should be sign. Okay? So I suppose that's also clear. That's another additional aspect that we can check out. Okay, so in the last slide, that's the sixth problem. The Fourier series coefficients of periodic signal xt expressed as, when it's given as periodic, Fourier series coefficients are present. Okay, xt is expressed as an exponential kind of Fourier series representation where k goes from minus infinity to plus infinity, ak e raised to j to n 2 pi kt by capital T, where T happens to be the period. Okay. And the coefficients are given as a minus 2, 2 minus j1, and a plus 2 as 2 plus j1. So they are complex conjugates. A minus 1, 0.5 plus j 0.2, and a1 is 0.5 minus j 0.2, and there's only a single one standing alone, that is a0 is equal to j2. Okay. So which of the following is true? Okay, so many options are there. So we'll go through each one of them. Xt has finite energy because only finitely many coefficients are non-zero. That's not right. This is true for, according to Pascal's theorem, this is true for power. Okay, it's not true for energy. So it has what is called as non-finite energy. Okay, so that's ruled out. Xt has non-zero value because it is periodic. Absolutely no, not true for all periodic signals. Okay, so let's move to the next one. The imaginary part of xt is constant. So just let us look at the imaginary components. Let us pick up the imaginary components. Okay, so from a minus 2 and a plus 2, we pick out a minus 2 and a plus 2, we pick out minus j out, and so we have e raised to minus j 2 omega naught t plus e raised to plus j 2 omega naught t, the coefficients. Okay, we are picking out the coefficients. Okay, and then we pick out from a1 and a minus 1 0.2 j, so we have e raised to minus j omega naught t minus e raised to plus j omega naught t, and then we also have plus j2. Okay, so what does these coefficients tell us? The coefficients of j tell us, they tell us that these are going to be, and so you can have plus j and minus j multiplying by, and the division by plus j and minus j, and also 2 for numerator and denominator. So you have a sign quantity. Okay, so you have sign quantity in both of these cases, which are of course which are constant in nature. Okay, so we see that this is what is, and j2 alone remains constant. It is not going to be it is not available because it does not have any t associated with. The other cases, we are going to have sin omega naught t. Okay, so those omega naught tells us that we are having the imaginary part of xt is going to be constant. Okay, the real part of it is not going to be constant because we will see that there is no j2 associated with it. Okay, then moving on to the seventh one, the last of the problems. Let xt be a periodic signal with period t. Let yt is equal to xt minus t0 plus xt plus t0 for some t0. The Fourier series coefficients of yt are denoted by bk. If bk equals 0 for all odd xk, then t0 can be equal to. Okay, so in this case, the best way to think in terms of addition of t0 and also removal of t0, and then allowing all the odd coefficients to go, all odd values to be nullified or go to 0. It's very clear that we can think in terms of any cosine functions or sine functions where an addition by pi by 2 makes a cosine value into a sine value, and a sine value into a cosine value. And so what happens is that we see that if you are looking at the four quadrants, we see that cosine values have a positive value in the first and the fourth quadrant, whereas the sine values have a positive quadrant in the have positive values in the first and second quadrant. So cancellations happen as a result of this, and so we see that dk equal to 0 is true for whenever we are having what are called as a step of whenever we are seeing that xt minus t0 or xt plus t0, when they are added together, this nullification happens so long as t0 is pi by 2 for cosine and sine function. This is just a case in point wherein which indicates other things also. And what is pi by 2? Pi by 2 is 1/4 the period of a sine or a cosine function. Okay, so from the different options, option B is quickly chosen as t by 4 because that's equal. That's exactly what we saw now because of the quadrant placement of cosine and sine values as a result of deduction or addition of a face angle, let's say in this case, or a face value by pi by 4 or pi by 2, or in this case t by 4. Okay, so this is all for in this session. What we saw may have been very different from markedly different from the last session, but whatever is understood, I hope will be useful for you, especially the periodic nature of Fourier series coefficients in the case of discrete time signals. Also, the special aspect of how certain signals can be assessed as odd or even symmetry along with their along with the half-wave symmetry, such that the even components of the square of the Fourier series can be nullified or removed from consideration. Okay, we also saw the interesting concept of an impulse train with alternating positive minus negative sign passing through a low pass filter, resulting in a cosine waveform. Okay. Yeah. So, and also the fact that whenever we are having special kinds of signals which appear to be periodic on only one side of the t equal to 0 axis, will have no Fourier series representations nor Fourier series coefficients. So, I suppose from this we'll move on to Fourier transform. Thank you.